Welcome to AP Chemistry. This is topic 2C for Unit 2, and we're going to talk about intra-bonding, so bonding in between the atoms in a compound. So intra-bonding, like intra-bonding is based upon Coulombic attraction, but the attractions here are relatively very strong, making intra-bonds much stronger than intermolecular forces. In general, there are two types of intra-bonds, ionic and covalent. Ionic bonding involves the transfer of electrons between atoms to form ions. When electrons are completely transferred, the electron cloud distribution can be thought of as thus. Atoms have equal numbers of protons and electrons and consequently have no overall charge. When atoms lose or gain electrons in order to achieve full S and P subshells or noble gas structure and relative stability, the proton and electron numbers are unbalanced, causing the particles to become charged. These charged particles are called ions. Since metals have a tendency to lose electrons to form positive ions, and nonmetals the opposite, the ionic bond is usually formed between metals and nonmetals, example, elements that are widely separated in the periodic table. These strong electrostatic forces between the charged particles are called ionic bonds. Since the electrostatic forces are large, the bond is a strong one, and since Coulomb's law predicts that force increases with increasing charge and decreasing distance between charges, the strongest ionic bonds are formed between ions that are small because they can get close to one another, and highly charged, example, one that have high charge densities. So ionic bonds. The ions present in an ionic solid are held rigidly in fixed positions in a giant three-dimensional lattice. These rigid structures mean that ionic compounds are not malleable or ductile and tend to be brittle, since when the ordered structure is disrupted, like charges repel and the solid splits apart. In the ionic structure, the lattice of ions is held together by strong electrostatic interactions between them. The strong bonds give ionic solids high melting and boiling points and low volatility, and subsequently low vapor pressures. Ionic substances can only conduct electricity when molten or in solution. Molten means it's in a liquid state. It's been melted because it's probably at a really high temperature. Since in the solid, the ions are rigidly held and cannot move. So this is what we're talking about. Some salts that are ionic bonds, and they're really held in place in a organized, structured manner. And then when we take these and dissolve them in water, some of them will, ionic compounds that split apart very well tend to conduct electricity. For example, this one's probably sugar. If you put sugar in water, it does not conduct electricity. And this one says it is distilled water. It does not conduct electricity. There's no ion particles in there to conduct electricity. So ionic solids dissolving. When an ionic solid dissolves, the polar water molecules are attracted to the oppositely charged ions and penetrate the lattice, attaching themselves to the ions. This is the idea of like dissolves like. The process is called hydration, and the ions are said to be hydrated. The ions become free to move when they are hydrated, and the solution will be a good conductor of electricity. Since a nonpolar solvent will not be attracted to the ions in an ionic solid, the ionic bonds holding the solid together are not broken and the solid will not dissolve. The hydration process increases the entropy or disorder. We haven't talked about entropy yet, but when we think of a letter for entropy, it is the letter S. So covalent bonding. In covalent bonding, electrons are shared between atoms to once again achieve a full S and P subshell, this time by joining together and sharing valence electrons. When they do so, they form discrete molecules. One shared pair of electrons represents a single covalent bond. Two shared pairs represents a double bond. These bonds usually occur between atoms that are nonmetals. Example, between elements that appear close to one another in the top right-hand corner of the periodic table. As we saw earlier, when the electrons are being perfectly shared, we can think of an electron distribution as this, or thus. In the simplest terms, it is possible to think of compounds being either 100% ionic or 100% covalent, but actually it's necessary to consider these two situations being at the extremities of a sliding scale. In fact, most bonds are intermediate between the two, with a largely covalent substance actually having a degree of ionic character or behavior, and vice versa. Ionic substance with some covalent character. If the cation is small and highly charged, it will have the ability to distort the charge cloud around the anion as thus. Comparing this diagram with the charge cloud representation of 100% ionic bonding and 100% covalent bonding, it is possible to observe the ionic bond beginning to acquire some covalent character. Feijton's rules to help predict ionic or covalent character help to assess the degree of distortion or polarization. Distortion will be at a maximum when 1. The cation is small and highly charged or has a high charge density, and 2. The anion is large and highly charged. I like how that rhymes. Example, electrons are more loosely held. So covalent substances with some ionic character are polar covalent. As we saw earlier, if one atom in a covalent bond has a higher electronegativity than the other, then the electrons are attracted toward the more electronegative atom, leading to an electron cloud distortion and a redistribution of electron charge density as thus. Using the Pauling scale of electronegativities, it is possible to make predictions about the degree of ionic and covalent character in a compound. By considering differences in the electronegativity and by using the table below, one can predict the percent of covalent and ionic character present in a bond between two atoms. A difference of approximately 1.7 marks the boundary between predominantly ionic or covalent character. Metal structures. Metallic bonding. A metal structure can be considered to be a close-packed lattice of positive atoms or ions surrounded by a sea of moving delocalized electrons. These electrons and their movement cause metals to be good conductors of electricity. The close-packed atoms or ions make them good conductors of heat. The metallic bond is the electrostatic attraction between the positive and negative charges. The flexibility of these bonds makes metals malleable and ductile. I do love a good metal, especially heavy metals. And that is the end of our intra-bonding.